In part 2 of section 18, we're going to look at the graphs of exponential functions, and we're going to be adding 2 new parent functions to our library of parent functions. This example here, 18.4, is going to give us the exponential growth parent function. I'm going to write that up here. This will be for exponential growth. And looking closer at the example, it says to graph f, and f has a domain of all real numbers given by the equation f of x equals 2 raised to the x, and that's how I can tell that it's growth, because I see the base value there is larger than 1. We'll take the same approach that we have with all other parent functions, and that is to create a table. I will select the following values: -3, -2, -1, 0, 1, 2, and 3. This should give us plenty of ordered pair to have a good understanding of what the behavior is going to be for the exponential growth function. The value that I'm going to start with is 1. So if I plug in 1 to the equation, I would have 2 raised to the first power, which is just going to be 2. X equals 2 will be the next one I go to, so I'll have 2 raised to the second, that's going to be equal to 4, and then 2 raised to the third, which is going to be equal to 8. Let me go ahead and plot these 3 points: 1, 2, 2, 4, as well as 3, 8. And I can already start to see a little bit of a curvature here, but I need to have some more points going off to the left into the negative x value part of my Cartesian coordinate plane to really understand how this curve is going to come together. Let's go to an x value of 0. This is going to be 2 raised to the 0. And there's a property of exponents that is supposed to have been discussed prior to being in college algebra, which is that anything that we have raised to the 0 is going to end up just being equivalent to 1. So that gives us the point at 0, 1, which actually serves as the y-intercept. Then we go on to the negative exponents. That would be 2 to the -1, 2 to the -2, and then 2 to the -3. So what we have to understand is that negative exponents are not the same as negative multipliers. So for example, if I was to say -1 times 2, that will give a negative result, -2. But if I say 2 raised to the negative first power, all that's going to do is cause me to have the reciprocal. So I would have to take this as 1 over 2 to the first power, which is just going to be 1/2. Doesn't make the answer negative at all, it just creates the reciprocal. So 2 to the -1 is equivalent to 1/2. Now I can do that same calculation with, say, 2 to the -2. So for this one, I would have to think of it as 1 over 2 squared, which is going to end up being 1/4. And then this makes it a little bit easier to think about 2 to the -3. I can always do the cube part first. I know what 2 to the third power is, that's 8. And then if I reciprocate that, I would end up with 1/8. So there's a nice connection here with the bottom input of 3, 8, and then this top input here with -3, 1/8. They have the reciprocal outputs, and then same thing happens here with -2, 1/4, very similar to 2, 4, and then we also have that happening with -1, 1/2, and +1 with +2. And then the only one that doesn't have a pair like that would be 0, because it just maps to 1. So let's plot these other points. We're going to have -1, 1/2, -2, 1/4, and then -3, 1/8. definitely a trend here. If I'm connecting these points together in a nice smooth curve, I'll see a increase as I'm going from left to right. Now all I've done so far is just try to connect these points, but the domain for this is all real numbers, so I need to continue the trend beyond the viewable window, and I can tell that going off to the left there's a horizontal asymptote because it's starting to approach the x-axis there. It's flattening out, which is similar to the behavior we saw with rational functions. So as I continue to go to the left, I should just be getting closer and closer to the x-axis, and then that's my boundary there. Going to the right, however, my graph is just going to continue to increase. I'm not approaching a vertical asymptote or anything because I can go as far to the right as I want, and it'll just continue to increase forever, and this gives us the graph of f. This is the go-to picture when we start talking about exponential growth. We are also asked to state the domain and the range. The domain of this function was given to us in the function definition. That would be all real numbers. But the range was not given to us. We have to observe the range from the graph, and the entire graph is above the x-axis, so that would be represented as 0 to infinity. And notice that I don't have a hard bracket on the 0 because I don't want to actually include the x-axis there. And then the last thing would be the writing the equation for any asymptotes. There is only one asymptote. It's a horizontal asymptote, and it is located at y equals 0.